Hello and welcome to a new video in a course on linear algebra. So we've recently started studying the topic of linear transformations, and in the previous video we mentioned that we need a little digression where we'll study some concepts related to sets of vectors. So in the previous video we defined what's so-called a span of a set of vectors, and we define it to be the set of all linear combinations of the vectors in that set, and namely finite linear combinations. And the purpose of this video is to define what's so-called a basis set. So given a vector space, there's what's so-called a basis set associated to that vector space, and we're gonna see what that means. But before we define what a basis set is and motivate it, we shall start by talking about the concept of linear independence, right? So if we want to say this in a few terms, in a few words, so given a vector space, V, right? And let's say it's equipped with addition and scalar multiplication, plus and dot, right? So a linearly independent, or let me just say, a linearly independent set V1 through Vk. So we have these vectors that are contained, that are coming from the vector space V. This set of vectors is said to be linearly independent if quote unquote no vector in the set, let's give this set a name. Let's say this is a set S. And the set S can be written as a linear combination of the others. So too many words here. What does that mean? Well, this means that if you take any vectors of these, right, this vector cannot be in the span of the other vectors. So let us take an example, probably, before we just restate the definition clearly or mathematically. Let us just take an example here of a set of linearly independent and linearly dependent sets, right? So here's an example. So let's take V to be R2. So V is gonna be the vector space R2, right? The set of all 2 by 2, the set of all 2 tuples, right? So let's take the vector 1, 0 and the vector 0, 1, right? And the question is the set linearly independent? Well, if you look at this, can you write any of these vectors as a linear combination of the other? What does that mean? If you take this vector, for example, can you find a constant, right? Is there a C such that when you multiply it by 1, 0, you get back 0, 1? So in a sense, you're writing here this vector as a linear combination of the others. Well, can you do that? Well, the answer is no. So this will force, like, the equality of this and this will force C to be 0 and 1 to be 0, which is kind of absurd, right? So this is a contradiction. So there isn't such a C. So there isn't such a C such that you can write one vector as a linear combination of the other, which means that this set is linearly independent because you cannot, right? So suppose we can write it as such, then we get a contradiction. In that case, I'm gonna go ahead and define to you the definition that we're gonna use in this course for linear independence. So a set S, right? A set S. So given a vector space V with addition and scalar multiplication. A set S containing vectors coming from V, right? Containing V1 through Vk. A set S of these vectors is said to be linearly dependent. Be careful here, I'm defining what linear dependence is. This set is said to be linearly dependent if there exist scalars, which means numbers in the real in the set of real numbers, R1 through Rk, such that if you take this linear combination of the V's from the set, you get zero. You get the zero vector, right? But I should stress that this is a non-trivial combination. So let me just give an example to refine what I just said. Okay, so let's take, for example, V to be the vector space R cubed, right? It's the set of three. It's the set of tuples of size 3, right? So let's take the set S to be the vectors 1, 2, 0, 2, 1, 2, 4, 0, and 0, 0, 1. And this is going to be contained in the set, the vector space V. Now, this set, which is contained in V, is linearly dependent. And let us check why is that the case. If you look at the second vector, you see that the second vector is just 2 times the first vector. And you can immediately conclude from this that this set is linearly dependent, because one vector could be written, this vector could be written as a linear combination of the other vectors, right? So this is a fairly linear combination of the other vectors, because this is 2 times this vector plus 0 times the other vector, right? Which is 0, 0, 1, right? So this is a linear combination of the 2 other vectors, and we could write this middle vector as that, which means that this set is linearly dependent, that this set is not linearly independent, it's actually linearly dependent, right? So maybe let's take another example before we wrap up this video and move to the next video where we discuss the basis of sets of vectors, where we discuss basis of vector spaces. So let's take another example, probably, because this is very important. Okay, so let's take a slightly harder example now. Let's take V to be the space of polynomials, right? So let's take P to be this is the space of polynomials. Okay, so we proved earlier that the space of polynomials, when equipped with addition and scalar multiplication, in the usual sense, in the usual way you add and multiply polynomials by constants. If you take this set of polynomials and equip it with these two operations, you get a vector space. This was proved probably in the first video or so, in this course. So if you take this vector space, and let's consider the vectors 1, x, and x squared, right? And why am I calling these vectors? Because remember, elements of the vector space are called vectors, right? So we're taking the vectors 1, which is the polynomial 1, the constant polynomial, and then we're taking the polynomial p of x equals to x, which is this polynomial of degree 1, and we're taking the polynomial x squared, or p of x equals to x squared, which is the polynomial of degree 2, and let's call this set S. And I claim, right, that S is linearly independent. So let us prove this. Well, here's a way of proving a set is linearly independent. So here's the way you would do it. Well, linear dependence means that you can find R1 through Rk such that when you add these and when you add the vectors and multiply them by the r's, you get 0. But for linear dependence to happen, it must be that not all of these are 0, right? Not all of them are 0. Now, otherwise, we say that the set is linearly independent. But what does that mean? It means that if you were to take such a linear combination and it is equal to 0, then it must be that all of these are zeros, right? So maybe it's worth it to state this here. So, i.e., S is linearly independent if for every R1 V1 plus R2 V2 plus dot 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 plus Rn Vn, if you take any such a linear combination, you put and it is equal to 0, then it must be the case that it's a trivial linear combination, right? It must be the case that all of the real numbers are zeros. So usually when you want to prove that a set S containing vectors v1 through vk is linearly independent, the way you would do it is that you start with such a linear combination and then you prove that all the r's must be 0, right? And how would you prove linear dependence? Well, to prove that, what you do is that you find such a linear combination, that is equal to 0, such that not all the r's are 0, right? So these are the ways of proving linear dependence and independence. And now let's go ahead and prove that this set is linearly independent, right? So we're working in the space of polynomials, and we have these three vectors, i.e. these three polynomials, and we're proving that these are linearly independent. Well, how would we prove that a set is linearly independent? Well, we take a linear combination we assume that this is a linear combination with value equal to 0, and this 0 is the 0 vector. But what is the 0 vector in the space of polynomials? Well, it's the 0 polynomial, right? It's the polynomial that's equal to 0 for every x, right? So it's p of x equal to 0 for every x. So the question is, or since we're proving linear independence, then this must imply, or we have to prove that all the r's are 0, right? However, this is clear. Why is this clear, right? So let's see why is this clear. So let's call this polynomial f of x, okay? Let's call this polynomial f of x. And let's take the derivative of f. What's the derivative of f? Well, the derivative of f is equal to the r1 will disappear. So this will disappear when we take the derivative with respect to x. It's going to be r2 from here plus 2 r3x. And since the right hand side is 0, this will also be 0, right? And now let's take another derivative. So let's take now the derivative of f prime of x, and if you take the derivative of that, it's gonna be, this thing will disappear and we'll be left with 2r3, and since the right hand side is 0, this is also gonna be 0. Okay, so 2r3 is equal to 0. This implies what? This implies that r3 is equal to 0, dividing both sides by 2, whatever. So let's enumerate. Let's call this equation 1, equation 2, equation 3. So now plug r3 equals 0, because we just proved that, in equation 2. Okay, if we plug this in equation 2, what do we get? We get that we have r2 plus 0 is equal to 0. Now, what does this mean? Well, this means that r2 is 0. Now, plug r2 equals r3 equals 0, because we just proved that in equation 1. What do you get? Well, you get you get here 0 and here 0, so it's going to be r1 plus 0 plus 0 equals to 0. And thus, this implies that r1 is 0. But what did we just prove? We just proved that r1 is equal to r2 is equal to r3 is equal to r3 is equal to 0, right? And this is what we wanted to prove in order to show that this set S is linearly independent. We started with any linear combination that is equal to 0, and we proved that this linear combination must be trivial. It must be that all of the coefficients we're taking are 0, right? Because otherwise these vectors will be linearly dependent, okay? And what was the motivation? Why did I take derivatives here? It's kind of annoying for you if you haven't seen this before. Well, the reason I took derivative is that first of all, you guys should know that a polynomial cannot be equal to 0 for every x unless like it's the 0 polynomial, right? This can't happen because from the fundamental theorem of algebra that a polynomial has only a finite number of roots. Anyways, I don't want to get this too complicated, but long story short, a polynomial cannot be 0 for every x without it being the 0 polynomial. And here I was proving to you that this must be the 0 polynomial. And usually when you want to prove a polynomial is 0, you prove that you prove every coefficient of it is 0. And I wanted to kind of isolate each coefficient alone. So one way of doing this is that you take a derivative, you take the derivative of this twice, of this thing twice, so that it becomes 0, and you'll be left with this, so that you show that this 0, and then you kind of undo the steps one by one to get that all the coefficients are 0, right? So this is what we got. So on the contrary, I should give you another example to convince you that this is not always the case. We can have linearly dependent polynomials. So let's take a final example here, just to convince you that polynomials can indeed be linearly dependent. A set of polynomials can also be linearly dependent. So let's also take the space of polynomials, V to be the space of polynomials, and let's take S to be x squared, and let's say x power 3 and x squared plus x power 3, right? If you take this set, well, this is certainly linearly dependent. Well, why is that? Because you can write one of the vectors as a linear combination of the others, right? x2 plus x power 2 plus x power 3 is like literally the first polynomial, this thing, plus x power 3. I mean, I've written the obvious, but this is literally like here we're talking about this element, and here we're talking about the linear combination 1 times this element plus 1 times this vector, and this is a linear combination. And thus, since you could write one element as a linear combination of the others, this means that the set is linearly dependent. Okay? Another way to see it is using the other definition, which is that you can take the combination minus 1 times x squared minus 1 times x cubed plus 1 times the vector x squared plus x cubed, and this is 0 clearly, right? You can look at it. Yeah, it's clearly 0, right? So and you just took this is R1, this is R2, and this is R3. Not all of them are zeros, and however the sum of these is 0, and thus you found a non-trivial linear combination which makes these linearly dependent. Anyways, next video will cover the topic of bases of vector spaces.